Okay, so let's say you need to calculate the longest increasing subsequence of a given sequence, and you want to do this fast, okay? So what we'll do today is we will use dynamic programming, actually two different approaches to solve this problem. First of all, we will see the slowest one, which is n squared, and then we will see the optimal one, which is NlogN. This is time complexity, okay? So first of all, what we'll do is read the length of our array as the input. We will use this to be our array. We use n+1 elements because we have one-based indexing. We start indexing our elements from number 1 until n. Okay, this is the DP array we will use, again with the same amount of elements. And this is just a for loop to read the elements in. In this case, we will consider that we read numbers, okay? So let's go ahead and see how the n squared solution works, okay? So the n squared solution, what dpi represents is the length of the longest decreasing subsequence up until index I, okay? So up until that index, what is the length of the longest decreasing subsequence, okay? So this is very straightforward, what dpi represents. So initially, for the first element, we just take itself. So the maximum length that we can achieve is 1, okay? The number itself, so one element, okay? And we know that by default, it has no previous elements, so there is no chance you can get better than 1, okay? So dp1 is solved. We will use this integer just to save the longest decreasing subsequence length we have found so far, okay? And then what you do is just you have two for loops, okay? The first for loop begins from the second number until the last one, okay? And what it does, it will calculate dpi. So it will calculate the best solution until index I, okay? Initially we set this to be 1, so this is the default. We just take the element by itself. So by itself is an increasing subsequence, okay? Of length 1, of course. And what we do is we just iterate through the previous elements, okay? It's only the previous elements we can add to the left of that element, okay? And what we do is this. For each element that we find this condition to be true, so that previous element, aj, is smaller than ai, then what we do is this. We update our best solution for index I to be the maximum of that solution we have so far, or we can use the solution for number j and add one element at the end of that solution. So the element ai, okay? We will add this element to the best solution for the element j, since number j is smaller than our element, okay? And of course we update the variable that we use to store the best result. And that's pretty much it. That's how the n squared solution works, okay? If you don't want a strictly increasing subsequence, you just add the equals sign right here, okay? So this is very straightforward. This is a very simple solution, the n squared solution. Okay, so let's jump in and check out how the NlogN solution works, okay? So how to calculate the NlogN solution is this. First of all, we will change the meaning of what dpi means, okay? So dpi, in this case, we will consider it to mean this: the smallest element that was so far the last element of a subsequence of length I. Sorry, so the smallest element that was so far the last element of a subsequence of length I, okay? And it will not be the index, it will be the actual element, the actual value of that element, okay? So the first element, of course, is going to be the smallest element for the first subsequence, the subsequence that uses just the first element. So then by default, dp1, so for the first element, is going to be itself, okay? This is going to be the best solution until that array of length 1. So what we'll do is we will use a variable to save the maximum length that we have reached so far. And we will do the following. Beginning from the second element, since we have already calculated for the first element, we will iterate until the last element. And what we will do is this. In the event that the best solution for the greatest array we have found so far, for the longest increasing subsequence we've found so far, if that specific element is smaller than our current element, what we do is this. We increase the answer we have found, so we increase the length of the longest increasing subsequence, and we set our element to be the last one, okay? So the smallest element for that specific length is our element, okay? Afterwards, in the case that we are not greater than the greatest, than the smallest element of the greatest length, what we do is this. We check if we are smaller than the first element. So if we are smaller than the first one, we just replace it, okay? It's pretty straightforward. If we are a smaller element, so we are a better solution for an array of length 1, okay? Otherwise, so in this case, we are neither greater than the last one, we are neither smaller than the first one, okay? So in this case, we are going to do a binary search. So this is the tricky part, so to speak, of this DP solution. So what you do is you set your left index to be 1 and your right index to be the maximum length. So yes, the rightmost element of our DP array. What you do is just a binary search. You say that until left is smaller than right, we need to find the immediate greater, so the smallest element that is greater than our current element, okay? So we take the middle, we check if the middle element of the DP array is smaller than our current element. If that's true, then we increase the left bound to be equal to middle plus 1. Remember that we need to find the immediate greater, okay? Otherwise, what we do is we check if the middle element is greater. So if it is greater, we want to keep it in our segment, but we do not want to go further than that mid element, okay? So we say the right bound is going to be equal to mid, okay? So that's it. That's pretty much the binary search. And now after the binary search is done, so index I will show the immediate greater element than us. So what we do is we check the element that is exactly left of that element, of that immediate greater element, and we will check if that element is smaller than our current element. What we do is we change our immediate greater with our current element. So the DP for the right index is going to be equal to AI. So we are smaller than, we know that for sure we're smaller than this element, and we are also greater than its previous best, okay? So we are the best element now for the subsequence, for the increasing subsequence of length right, okay? So again, if you do not want this to be strictly increasing, you just can change the condition here. You can make this equal. You will do the same here as well. When you check for if you are greater than the greatest, you can do this here as well. Okay, and that will give you the increasing subsequence, not the strictly increasing subsequence. But in this case, we do the strictly increasing subsequence. Okay, so that's pretty much the code. The code will be in a GitHub link in the description. You can find down below the video. And now let's go ahead and check out some examples to see how this algorithm actually works, okay? So again, we take the first element. The first element is the best answer for the first index, for the length of number 1, okay? We go to the next element, number 2. Number 2 is greater than 1, so we write this here. Number 3 is greater than 2, we write this here. Number 1, we do binary search. We come here, we can see that the immediate greater is this one, number 2, but the immediate previous is equal to ourselves, so it's not smaller, so we do nothing, okay? So we go to the next one, number 2. Number 2 again, it's the same. You do binary search, you find the immediate greater, but the immediate previous is equal to ourselves, so we do not change nothing. We go to the next one, number 3. 3 is equal to the greatest, so in this case, what the code will do here is this. So you see that it is not smaller. You do the binary search, and the immediate right that you will get is going to be 3 again. It's going actually to be this one. But since it is not, even if it is smaller than what we are, and that we will change this to 3, so it remains the same. Okay, there is no harm from our binary search. Our binary search works correctly. Okay, so we go to the next one, number 7. Number 7 is greatest than or greater, so new personal best for our subsequence. We go to the next one, number 3. Number 3, again, you do binary search. You see that the immediate greater is number 7, so the previous number is 3. It's not smaller, so you do no change. Okay, we go to number 4. Number 4, you come here. Okay, so you do a binary search again. So the immediate greater is this. You see that the previous is 3. So 3, yes, 3 is smaller than 4. So what you do is you erase 7 and you put 4. Okay, you go to number 5. 5 is greater than our greatest, so 5 here. 8 is also greater than our greatest, so it goes here. So the longest decreasing subsequence you can get is of length 6. Okay. Okay, so this is the one example. So let's go to the next one. So in this example, let's see if this example is better. So first number is 1. Again, you just pick a red color. Okay, so number 1. Number 3 is greater than our greatest. 6 greater than our greatest. 4, you do binary search. You see the immediate greater is 6. So the previous is 3. 3 is smaller than 4. So what you do is you go to the immediate greater, you delete that element, and you switch it with number 4. Okay, we're until here. So the next one is number 3. You go to number 3, immediate greater is 4. The exact element to the left is 3, so it is not smaller, so you do no change. You go to the next one, number 5. So number 5 is greater than our greatest, so it comes here. You go to the next one, number 7, greater than our greatest, so it goes here. You go to number 2. So number 2, you go to the immediate greater, which is number 3. You check with number 1. So number 1 is smaller. So since it is smaller than our element, which is number 2, you can switch the immediate greatest and make it number 2. Okay. So the smallest element for a subsequence of length 2 is number 2. Okay. So we go to number 1. Number 1, immediate greatest is 1. Immediate previous is 1, so it is equal to that number, so we do no change. We go to number 8. Number 8 is greater than our greater. Number 9 is greater than our greatest. So let's say we have number 6 here, just to clarify again how it works. So number 6, the immediate greater is number 7. Okay, the previous of that number is number 5. Number 5 is smaller than 6. Okay, so what you would do is you change this 7 and you make it a 6. Okay, because there is a better subsequence of length 5 if it ends to 6. Okay, so this is how actually the second solution, the NlogN solution for the dynamic programming works. Okay, so again, I will leave this code in the description in a GitHub link. I have also 2 problems here that I will leave in the description here, where you can check your solutions. The first link works with the n² solution, and the second link works with the NlogN solution. So if you like this video, give it a thumbs up, subscribe to the channel, guys, and I will see you in whatever I will be making next. Goodbye.